In this video, we're going to be looking at how to do implicit differentiation. So let's get started with this example over here. The first step we always try to do whenever we do implicit differentiation is see if we can do it implicitly. And what I mean by that is, can I rearrange this equation to make it look like y equals something in terms of x? If I can't do that, like in this example, then I would have to use implicit differentiation. Implicit differentiation works the same as normal differentiation, but with a minor difference. So I'm going to differentiate each term here separately and show you what's going on. So if I wanted to differentiate x squared normally, I would say, using the power rule, that would just be 2x. So far nothing has changed really. I've just differentiated the first term as is, but it changes with this term over here. If I wanted to differentiate xy, and I wanted to do it with respect to x, then I would have to use product rule, because I'm multiplying two different functions together. So using the product rule, I would say we would keep the x and differentiate the y, so that would just be x. And then we would do minus, keep the y, but differentiate the x. So this is exactly what it would be if I used the product rule. However, in this first step over here, I differentiated y. So in other words, I differentiated the y, and I said that was 1. However, that's incorrect. If I wanted to actually differentiate this with respect to x, I would actually have to multiply it by dy over dx. So that's the only difference. If that didn't make sense, let's continue on with this question. In order to differentiate cosine y, we know that the derivative of cos is negative sine. So this would just be plus negative sine, which is the same thing as negative sine of y. But this time, because I've differentiated the y instead of the x, I just have to multiply it by dy on dx. It's that simple. And finally, on this side, the derivative of 6y would just be 6, but because I'm differentiating y instead of x, we just have to times it by dy on dx. And the derivative of x squared is just 2x. So that's how you differentiate a function that you cannot rewrite in terms of y. So now all we have to do to find dy on dx is rearrange this equation. And the way I'm going to differentiate this equation, rearrange this equation, is I'm going to bring everything with a dy on dx to one side of the equation. And now I can bring this to the other side by minusing. And I can bring these two terms over to the other side. And this just simplifies down to minus y. Now I can factorize. I can factorize this by pulling out a dy on dx, and I will be left with minus x minus sine y and minus 6. And that is equal to minus y. So now if I wanted to find what dy on dx is, I can just rearrange. I can say this is just minus y divided by minus x, take sine y, take 6, and that is the derivative. If you're interested in simplifying, this would simplify to y divided by x plus sine y plus 6. And that's how you implicitly differentiate. Let's have a look at another example. This time we have a fraction, and you can pause the video and check, but trying to rearrange this equation for y is very, very difficult. And so I'm going to use implicit differentiation here. So we're going to differentiate the left-hand side first. And because we have a fraction, we need to use the quotient rule. And when we use the quotient rule, the first step we do is we copy down the denominator on the top and the bottom. But on the bottom, we just square it. Then we just have to differentiate the numerator. So the derivative of the numerator is 3x squared, which is 6x, and plus 2y is plus 2. But look, we've accidentally differentiated a y instead. So we just have to times this by dy on dx instead. Then we have to minus away the opposite step. So now we're differentiating the denominator. The derivative of e to the power of y is just e to the power of y. But because we've differentiated y instead of x, we just have to times by dy on dx. And the derivative of 1 is just 0, so we're going to leave it as that. And then we just copy down the numerator back again. Just like that. And the derivative of the right-hand side is going to be just 0, because the derivative of any constant is always 0. Now I can factorize the numerator. Or I can expand first. So now what I'm going to do is expand the top and say e to the power of y, 6x e to the power of y, plus 2e to the power of y dy on dx. And I'm using the claw method or the FOIL method, whichever way you'd prefer, plus 6x plus 2 dy on dx. And now the other expansion is going to be 3x squared e to the power of y dy on dx minus 2y e to the power of y dy on dx. And because we're differentiating and we want to have just one equation, I would recommend you times both sides by the denominator here, because when we do that, we'll just be left with the numerator. So I'll just have equals 0, because I'm timesing both sides by the denominator. Now that we have this step, I can do exactly what I did in the first question. I can factorize out dy on dx, and this would just be 2e to the power of y plus 2, take 3x squared e to the power of y minus 2y e to the power of y. And I'm going to bring this term to the other side, because those are the only terms I have without dy on dx. And so on the other side, they would become minus 6x e to the power of y minus 6x. And now it's just a matter of simplification. I can divide both sides by that huge bracket over here, and I'll be left with minus 6 e to the power of y, take 6x, divided by 2e to the power of y plus 2, take 3x squared e to the power of y minus 2y e to the power of y. And there we have it. That's how we implicitly differentiate. Even though the working out looks very, very messy and very long and very complicated, the steps are always the same. First, you have to differentiate as you normally would, so I would use quotient rule. Then you just have to make sure whenever you differentiate y, you just have to times by dy on dx. So that's how you implicitly differentiate.